Hi everybody, welcome to the first lecture of Chemistry 211. Actually not Chemistry 211. Well, it sort of feels like that, but really what it feels like is Orgoland. Because organic chemistry is like going to a foreign country where you've never spoken the language before, and so we are going to learn how to speak Orgo in Orgoland. And therefore, you're going to be my guided tour of Orgoland. I don't mind being your tour guide. I love Orgoland like all tour guides do, and therefore you're going to become a great tour group and venture into Orgoland with each other. Okay, so let's start. Our view into Orgoland starts with a little welcome to the general picture of what Orgo land is all about. And the main focus of Orgoland, as you probably know, is going to be nothing but carbons and hydrogens. And we do dabble in a little bit of these other elements over here, but our real purpose in Orgoland is to study the structure, properties, reactions, shape, function of all of these different organic molecules and how they behave with one another in an organic universe. There are other elements to play with too. But I want to give you a little sense of what the overall goal of the course will be is something like this bizarre looking synthesis on the right here. That synthesis over there is got structures in it, and again, all the lines we're going to become familiar with in today's class. And really the overall goal is to build molecules and build functional groups and different molecules in Orgoland. So anybody know what we're making down there on the bottom over there of this synthesis, what the goal of this synthesis was? If you recognize it, you might be a fan of Breaking Bad. Yes, that is methamphetamine. That is the blue meth from Breaking Bad. So a lot of organic chemistry has a little bit of a bad rep because there are these illicit drugs out there in the world that are all made through organic chemistry. But there are lots of other fun drugs that are made that are definitely legal, and we can't do without them in our life. So here's one, and 2,4-isobutylphenyl propanoic acid. You're probably thinking, I've never taken anything with a label like that. I've never taken anything on that even sounds like that. I bet you have. So what drug companies do to make these organic compounds and drugs a little less scary is they sometimes take the actual chemical name, which we're going to learn to play with in Orgoland and be versed in, and they take this name and they turn it into ibuprofen. So yes, you've had this very long chemical drug. And the one thing is, you can see the picture of it now. It looks all flat and boring, but this is just to help us understand its connectivity, where in reality, it has got a lot of three-dimensional shape to it. This is not ibuprofen, sorry, but just another molecule of three-dimensional versions. And that's what we're going to try to do in Orgoland, is not only look at molecules, but try to visualize them in 3 dimensions. So for the next couple classes, let's review what is really necessary to be able to build organic molecules and play with them. And that's to start with LewisDot structures. So hopefully I'm tweaking your memory here. If you want a little more review on Intro Chem, please check out the Sakai site. There is a folder there labeled Review of Chem 105 material, essentially Intro Chem material. And you can go take a look at those websites, and they'll refresh your memories on such a thing like this, like LewisDot structures. Very cool. So how do we build molecules using LewisDot structures? What are all these dots? Remember, these are the valence electrons. And what you want to do to be able to remember the valence electrons is find a periodic table. I highly recommend that you print one out, get your favorite colored version of a periodic table, and plaster it right in front of you somewhere so that you can always have access to it. So what would be a molecule that we could generate with this set of atoms that would satisfy the octet rule and become a legal binding structure as a possibility? So for me, as you can see, carbon has 4 valence electrons spread out. Carbon is going to be the center of my world. Surprise, surprise, welcome to Orgoland. And therefore, the very first bond I'm going to make between two valence dot is going to be between two carbons. Everybody does Lewis dot structures slightly differently. Sometimes you guys add up all the electrons and just throw them together. But I think in a Orgoland universe where carbon is our central focus and generally the center of the molecule, that you might want to start building your molecules from the carbons out. So now I have my two carbons, and now I can start filling them in with hydrogens and the one oxygen. Okay? So there's maybe lots of possible structures for this one. I'm just going to play around and start adding hydrogens and make a bond here and start adding hydrogens to one carbon. So each of the hydrogens comes in and forms a bond with two electrons. And now I have one hydrogen left. So I put a hydrogen down here and one oxygen left. So I can make an oxygen bond here, but oxygen with its valence electrons of 6. So if I just do single bonds everywhere, this is not a very happy molecule. As you can see, the carbon doesn't have an octet, neither does the oxygen. And so at the very end, this carbon and this oxygen can come together and throw themselves together to make a double bonded O. So that's a little messy, I apologize. But now every atom has an octet of electrons around it. Lewis dot structures are just a model. They're not exactly the exact, I mean, this is not the way this molecule actually came to being, but it helps us understand connectivity. And as any model, there are sometimes exceptions to this model. But in general, for carbon, hydrogen, and oxygen, Lewis dot structures are going to take us very far. Okay. Try creating a Lewis dot structure with this set of atoms, and this one, I'm going to reserve all the answers to this one for our class, which, as you know, is going to meet as little small study groups, and therefore you can come in early or before the beginning of your scheduled meeting time with me and try this one with your study group, and then see if you can answer each other's questions, and then leave only those really, really toughies for when I show up to your study group. Okay? Cool. Now that we're our masters at Lewis dot structures, it is supposed to be review, so go play some more with them if you still feel a little rocky. It's okay. The other thing I mentioned about Orgoland is shape. That shape is going to matter. How these molecules behave definitely depends on their shape and location of all their atoms. So let's review VSEPR geometries. Some of these you can see are going to be very popular. This molecule, MgCl2, magnesium chloride, doesn't have any carbon in it, but it is a perfect example of a linear molecule. And notice how this molecule does not satisfy the octet rule. That happens with some of those metals way over there on the other side of the periodic table. We'll play with those very rarely, but sometimes. Boron trichloride has this shape to it. Notice we're spreading out all the atoms. What would you call this one? Yeah, you got it. Yes, yes. That's right, trigonoplanar. Good. See, those intro chem memory cells are firing off now. Very cool. All right, here's a good one. What about methane? What shape would methane have? Yep, tetrahedral. See, these are all things that are coming back to you little by little. And again, this is, as you can see, the only one with carbon in it. This is going to be our poster child for this course. We are going to want to display our carbons in two-dimensional paper. Notice it's got some weird wedge, dark wedge, a dotted line, and 109.5 bond degree angles. So trying to represent our three-dimensional molecules on a two-dimensional sheet of paper is going to be the ultimate challenge for you in Orgoland. And me too. These other ones down here with 5 VSEPR pairs or 6 VSEPR pairs are rarely used, but I definitely thought, oh, you would want to know, you'd want to remember, oh yeah, octahedral. Okay, so just for fun, we're going to throw those in there. They rarely show up in Orgoland. So these shapes are rare. You won't see them much. Now, already you have seen structures that look like this with lines all over them. And so what I want to do is make sure we're clear about how to represent organic molecules in lots of different ways that you'll see. You see the molecular model images are over there. They're trying to represent what these molecular model kits would generate if you built your actual structures with molecular model kits. I highly recommend that you try to borrow, beg, and steal to get a molecular model kit somewhere. And if you can't get one of these fancy-dancy molecular model kits, please feel free to use mini marshmallows and toothpicks. My kids had a lot of fun learning Orgo that way. Well, okay, maybe not so much Orgo with my kids. I had a lot of fun learning Orgo with my kids with mini marshmallows and toothpicks. So let's be very clear about all the different ways that we can represent the exact same structure. The line structure is the full blown out version. Okay, this is nice. It includes every single atom and every single bond. But then textbook companies had trouble writing this version on a line, and so they created the actual condensed version. Now, what I want you to pay close attention to here is the connectivity. Even though they wrote CH3CH, this does not mean the H is connected to the C, like 3 hydrogens are connected to the C, which then on the end is connected to a C. There's no H3 connected in between the two C's. As you can see, the 2 carbons are connected to each other, and then they fill on the outside. So this is, again, is just a textbook notation where they trust that you are an Orgoland expert and understand that carbons make up this backbone and the hydrogens are filling in the outside. So you might also see this written as H3C, CH2, and so on, to try to help the reader understand that these H's are on the outside, not in between the 2 carbons. If you don't want to write all those H's, then welcome to the skeletal structure. As you saw in the very first slide for our synthesis of methamphetamine, it's very fast and easy to start drawing just lines, as long as we're really clear what every line means. Every line means a bond, every vertices is a carbon, and we know now in Orgoland that every carbon wants 4 bonds. So if you don't see a carbon with 4 bonds, like this one on the end, then you know that the one on the end must have 3 hydrogens associated to it. Okay? If I put a carbon on the other end of this molecule, it's got 2 bonds coming to it. I know there's 2 hydrogens that are associated with it. So you can always blow these structures out from skeletal structures. They are the lazy man's way of drawing structures in Orgoland, and you will find that we are very relaxed and very lazy when it comes to drawing structures in Orgo. But to fully get the picture, which I want you to be able to do, you need to know that they are all full of hydrogens here. Okay, so you can see I've done that for several down here. See if you can do the condensed structure here. Take a second, pause, and I'll try to do this during the video as much as possible because I'm hoping you're like my college-age sons. They told me they watch all their lecture class videos at 2 times speed and just fly until their professor says stop or gives them a sign that there's a problem to do. Feel free to do the same with mine. Believe me, I will not be personally offended if you run these videos at 2 times speed. Okay, so try this problem. Ready, stop. Okay, here comes the answer. Were you able to fill it out with CH2s everywhere? And that's what this structure is. This is cyclopentane. Ooh, the name of a molecule. We are going to start learning nomenclature, meaning naming of compounds, coming up soon. Okay. Notice that the bottom one has the same number of carbons and hydrogens. So we're also going to learn about molecules that have the same number of carbons and hydrogens, but are built differently. Ooh, that's like a tease. That's like next week's thriller. Learn how, yeah, okay, all right. Sorry, I get carried away. Okay, this molecule is the skeletal structure, is the line structure for a certain compound. Please feel free, see if you can actually draw the skeletal structure for this one. I'll give you a minute. Pause. Okay, go. Did you come up with the following? you are going to get very good at drawing 6 carbons in a ring. But this ring has double bonds, every other carbon bond, and notice I just go out and that had 3 carbons on its chain, and so I only need 3 lines total. And at the end of each of those lines is a CH3. And that was a very quick way of drawing the compound above. Okay? So we just saw how drawing them in 2-dimensional, we can draw these lines, as you can see on the over there, up there, sorry, that you could draw methane like this, but this is not a very good representation of how this actual molecule exists. So what we're going to try to do is draw tetrahedral carbons in 2-dimensional space as close as possible. So we saw this up in the methane example for tetrahedral and the Vesper. Notice that it is best to draw it in a 3-dimensional space where we're going to say the wedge is coming out at you, out of the screen, and the dotted line is going away from you. And that the 2 lines here are actually in the plane of the actual screen or piece of paper. So it's a way of trying to express 3-dimensional geometry. One little quick note. I always start with my 109 degree at bond angle in the plane of the paper, because what's really important is every wedge and dotted line needs to be on the same side. So I can't have a wedge on one side of my line and a dotted line on the other side of the molecule, because that would not represent a tetrahedral geometry. That would be a little crazy. Try it with your molecular models and see that it really doesn't matter. You could draw it like this, and as long as your wedge and dotted line are on the same side of the drawing, then you've drawn a tetrahedral carbon. Okay, well, let's see how we do down here. See if you can draw the structure of ethane, C2H6, using lines, wedges, and dotted lines as bonds. Stop. Okay, let's go. I would then start with my 2 carbons in the middle. Okay, and then I can draw hydrogens up and down. You will see this is the preferred method, but it really didn't matter if you put them both on the same side, both pointing up, both pointing down. But all of these bonds, this H, this C, this C, this H, they are all in the same plane of the paper or the screen. And now I need my wedge and dotted line to express 3-dimensional geometry and a tetrahedral carbon here. Notice I need the dotted line and wedge over here. It really doesn't matter which one comes out first or second. You know, do you write the dotted line on the bottom? You can do that. And the wedge on top. Ooh, that's a bad wedge. Sorry. Ooh. Oh my goodness. Okay. I'm going to stop while I'm behind. Okay. So there's a there's no preference as long as the wedge and dotted line are on the same side. Cool. I hope you came up with this. All right, we're going fast and furious. So we have seen LewisDot structures. We've seen how to represent tetrahedral carbons and all the different kind of line structures that you can create. Now, the next most important part about our molecules and understanding how organic chemistry molecules behave with one another is charge. So I'm about to give you the answer to every question on the final exam. Wait, did you hear that at 2 times speed? The answer to every question on the final exam is this. Plus, loves, minus. Everybody says organic chemistry is hard, but in the end, if we're trying to determine how molecules fall in love with each other and make new molecules, like the synthesis of methamphetamine or the synthesis of ibuprofen, the only way you'll be able to do that synthesis is not memorize the entire textbook of organic chemistry reactions, but to recognize that if I can identify the positive and negative charges on a molecule, even the partial positives and partial negatives, then I'll be successful, because I'll never have two positives reacting with each other or two negative charges reacting with each other, just pluses and minuses. So formal charge plays a big role in organic chemistry. So let's make sure we know how to do this. There is a beautiful formula for the, oops, whoa, what happened? Okay, sorry, technical glitch. There is a beautiful formula for this. Oh, another technical glitch. Let's see what's going on. Ah, come back. Where are we? We're here. We're halfway through. Woohoo. Wow, this is exciting. Okay. Let's see if this works. Yay, we're back. Okay. This will just be the first of many technical glitches that occur. All right. So this is the formula the textbook wants you to use to determine the charge of every atom that's in a molecule. So if the molecule is charged overall, it means one of the atoms in the molecule has that charge, or the sum of all these formal charges within the molecule has to add up to this charge. Now, I'm really bad with formulas. As you can see, even technology, oh my God. So I would love to be able to determine formal charge without this formula, and there's a way to do that. Especially if you know the number of valence electrons that something like the carbon atom or the nitrogen atom is coming into the molecule with. If you know that carbon starts with 4 valence electrons, then I can look at this molecule and recognize that carbon literally feels like it owns 5. It literally feels like it owns 5 electrons total, which means it feels like it gained 1. So this carbon has a -1 formal charge. No formula. Woohoo! But that means you also have to remember or have a periodic table handy so that you remember that nitrogen comes into any molecule with 5 valence electrons. And if you look carefully here, the nitrogen actually has 5 valence electrons. So it doesn't have any formal charge at all. This is really important because then this tells us that this carbon, the carbon in the end of this molecule, is feeling a little negative, and therefore it is going to be attracted in the piece that will want to react with a positive piece of a molecule. And so you know how this molecule might want to react. Cool, huh? All right, let's play around with this one on the other side. Yes, let's do that. I was checking to see if this was a class 1 or not, but it's not. So take a second. Okay, let's go play. Did you try it yet? Good. Okay. This is what I got. See if you got the same. This carbon feels like it owns 5. So this carbon feels like it's a -1 charge. That means if the overall molecule is neutral, some atom in here has to be a +1 charge. So I go where it looks funny. Trust your chemical instincts. They will take you far in Orgoland. You guys are here for a reason. You've had some chemistry. So what looks a little odd is this oxygen, because I'm used to seeing oxygen with 2 lone pairs and 2 single electrons. That's its valence shell. So this one looks like it has a little lacking. It's shared a little too many. It only feels 5 electrons around it. So it is a +1 charge. Okay? So these are the formal charges. You can check on me on that carbon. It has 4 bonds to it, just like a tetrahedral. Carbon has 4 bonds. It is a 0 charge. All right. Now, this is not a very happy molecule. This has a negatively charged carbon and a positively charged oxygen. So after you make sure all the charges sum up to equal the charge of the molecule, the next thing you will want to look at is resonance. You might have denied this in the past, but resonance is a structure that, resonance is an idea that we will use a lot in Orgoland. So don't deny it. We're going to play with it a lot. You'll get really comfy with it the more you play with it. Resonance is a way, as we'll talk about in a lecture coming up, of having to spread the electrons around and move the charge around. So this carbon being -1 would love to donate and get rid of that charge and ownership and make a bond with that pair of electrons. But in doing so, it would then make too many bonds on this carbon. Whoa, come back. On this carbon. And so this one is exactly what that oxygen wants, since it's +1 and hates to be positive because it's electronegative oxygen, grabs the pair. So a better structure for this molecule, which will reduce the formal charge of every atom to 0, is as follows. Every single atom in this new molecule, this resonance structure of this molecule, is 0. This is a much happier, more stable molecule, and this is the way this molecule exists 99% of the time. 1% of the time it can do this, even though it doesn't like to, just to show that it can spread charge around. And so what we'll do at the end is to say, well, due to these resonance structures, you might be able to put some partial charges on this and look at how it behaves. We'll talk about that more in another lecture. So please take a moment for class to determine the formal charge of every atom in this structure if you'd like, but specifically the one circled with the nitrogen there. And please bring any structures to class where you're not quite sure what the formal charges are, and we can play with them in class. Dipole moments. They are a way that generate charge in a molecule that are not necessarily due to resonance structures. So they're not full negatives or full positives. They are partial. So we use these little arrows. I like how the end of the dipole moment arrow is a positive sign to show what the direction is of the charge. Okay, so if we start with carbon monoxide, you can prove me right or wrong, but I think that's the LewisDot structure for carbon monoxide. I think, yes. Okay, so what would be the dipole moment for this? And dipole moments use electronegativities. Okay, so you need your periodic table to recognize that electronegativity, the most electronegative atom is the fluoride, and therefore everybody wants, the fluoride wants electron density the most, then oxygen, then carbon. And so if oxygen is more electronegative than the carbon, then we have a dipole moment like this. And one way to express this dipole moment, so you don't have to draw these little dipole moment arrows everywhere in your molecule, is you can always just use these little delta minus and delta plus symbols to represent partial charge. Like that oxygen is pulling on those electrons in that triple bond a little more than the carbon is. So it feels like it has a little more electron density than the carbon according to electronegativities and the dipole moment. Try drawing the formal charge for this molecule. What's the formal charge of these two atoms? And then try doing the same thing with the methanol over here. We'll look at this one in class and see what your answers come out to be. As the little note down there says at the very bottom of the screen, if electronegativities and formal charge contradict each other, meaning something looks positive when it's got a dipole moment that says it should be negative, we trust formal charge. Reason is, electronegativities are as if the atom was in a space all by itself, not influenced by any other atoms around it, just its own personality. But as soon as it makes a molecule, the molecule then starts averaging out all the pluses and minuses and desires and whims and wishes of every atom to create formal charge. Okay, so trust formal charge. Cool. All right, coming to the end here. A few little things. Please understand that all these charges are going to cause things to be attracted. So this slide should look very familiar to you and not too surprising. That if we have two ions they create an ionic bond. So I'm going to spend very little time on this. Please bring it up in our study groups if it at all is like not clear. As soon as I go away from an ion, then I get to something like water, where I do have things that are dipole moments, and even water has very strong dipole moments and lots of partial charges, but they are not fully negative or fully positive, so they can still have an attraction to an ion. This is fairly strong. Now we come into the world, as you can see, of organic molecules. So these two organic molecules, they do have dipole moments, and they can line up so that their partial negatives and partial positive tails line up with each other and create this very weak 5 kilocal per mole, and we'll talk about how weak that is, weak interaction. But there's even weaker ones. Like, what if I put something that should be actually non-polar, no dipole moment? This is iodine, I2. There's no reason for there to be a pole or a dipole in I2 until I put it into a beaker full of water. And water has so many dipole moments that it pulls the charge apart in I2 and makes one end a little polar and a little less polar on the other. So it induces a dipole. Very weak interaction. And the weakest of all is if you were to put two very non-polar molecules together, and they have electrons and they have nuclei that are positive, they sometimes can spread the charge out a little bit. These last three are the very weakest, and they're called van der Waals forces if you don't remember, and they're probably the most popular that we will use in Orgo. And out of all of those van der Waals forces, I want to highlight one that is a very popular and relatively strong interaction, and that is this hydrogen bonding, which has to occur within molecules that have OHs or NHs, because anything with an NH or an OH has a hydrogen attached to an atom with a lone pair. Hydrogen, atom, lone pair. These are things that can then exchange their hydrogens and create, as you know, with water, for example, a little spider web of dipole moments and hydrogen bonding and dipole-dipole interactions. Okay? We think of these hydrogen bonds as being stronger than the rest, and now here comes the takeaway message. They're about 2 to 7 kilocals per mole to break a hydrogen bond. We're going to come back to this number a lot. Room temperature is about 20 kilocals per mole. So we're breaking these hydrogen bonds all the time with a beaker of water or a glass of water sitting around. They never are as strong as a covalent bond or polar covalent bond. Okay? But they're popular and cause charge. So this last one is a question. The intermolecular interactions between molecules of ethanol include. Stop, give yourself a chance to try it. Go. The answer is D. If you got some other answer, bring it to class. Let's talk about it in class. That's where we can answer all these cool questions. Last but not least in this lecture, which is rather long, one of the longer ones, I apologize, but I'm so excited about this intro chem and how it ties into everything. This is now the first slide. I'm very excited to get to this one because it starts to introduce you to the language of Orgo. All of the molecules we've been looking at, like ethane, methanol, these all have different pieces to them that make their chemistry slightly different. And the sooner we can recognize what kind of piece is in our molecule, known as a functional group, what kind of different functional group is in our molecule, the sooner we will be able to identify how they behave. For example, carboxylic acids have the word acids in them. None of the others have the word acid in them. So this functional group, whenever you see this piece here, actually has acidity to it, which we'll talk about in an upcoming lecture. And therefore, it's important to be able to spy this as being different from, say, an ester, or different than an amide, or different than an aldehyde. See all these other ones with the C double bond O in them. They have slightly different things to them, and they will behave slightly different. The sooner you know what an aldehyde, a ketone, a carboxylic acid is, as soon as you know these, the better off you are. So you can actually make flashcards of these right now, start doing it, but I have another idea for you. You got Post-it notes? Because if you have Post-it notes, then I recommend you do the following. Look at behind me. You might have not noticed because they were so tiny. Oh, but sitting behind me, I have Post-it notes on my office desk, right above my office desk, of all the functional groups that, a lot of them, that I need to know for this class. And so instead of memorizing all of these functional groups on boring little index cards, I highly recommend you just take Post-it notes and you write these functional groups and their piece and just put them everywhere, like your mirror where you get ready in the morning, brushing your teeth. Oh, there's a carboxylic acid. It'll just be, you'll see it every day, and you will start learning Orgoland language along with everybody else that's in your space, because you are going to Post-it note the heck out of your room, your space, and everybody's going to know that you're taking a tour of Orgoland this term, this summer. So please give that a try, and hopefully we'll get these under our belt in no time at all. Okay? Great. I'll see you soon during our scheduled study group time in our class. And please, again, feel free to come before your scheduled time, stay after your scheduled time, and even outside of your scheduled time, come wander into another study group and see what they're working on. Okay? All right. I hope you have a great day. I'll see you soon. Bye.